So in this video, we're going to quickly go over an example of how to apply the separable equations method to solving a differential equation in Calculus B. So for us, the example we're going to think about is this following differential equation. And remember, a differential equation is an equation that involves at least one derivative sitting there. So for us, that derivative is dy dx. And again, the right-hand side of this equation tells us basically how that function y changes with respect to x. So we're given this differential equation right off the bat. And the last thing I'm going to do here is say, well, this differential equation we're given, we're going to solve for y in terms of x, but we're also going to be given this initial condition, say y at x equals 0, and let's let this equal to 1. So this little piece here is what we call the initial condition, or the initial value. So let's apply the separable equations method. And the name of the game for this separable equations method, as the name suggests, we're going to try and separate the different variables onto different sides of the equation. Now, this seems a little bit trickier than it actually is. So for example, I'm just going to rewrite our equation. I'm down here, dy dx is equal to x squared minus 1 times e to the minus y. What we want to do is try to get all the y information on one side and all the x information on the other side. So what that means for us is we want a dy on one side, a dx on the other side, all the x stuff with the dx, all the y stuff with the dy. So the first move we're going to make is just multiplying x onto both, or dx onto both sides of the equation. So we have dx or dy is equal to x squared minus 1 times e to the minus y, all times dx. Again, we just cross-multiplied that dx onto the right-hand side of this equation. Now, the next move we get to make, though, is we have to ask ourselves, are all the y's on one side, or are all the x's on the other side? And well, for us, we see that we have that one term involving y, that e to the minus y. So what we can do next is divide both sides by e to the minus y. And then that'll give us all the y information on the left side and all the x information on the right side. So I want us to pay attention here to the fact that now we have all the y stuff on one side, all the x stuff on the other side. The other thing I want us to pay attention to here is on one side we have a dy, on the other side we have this dx. And the next move we get to make is, well, of course, this is an application of integration. We get to just apply the integral to both sides. So if we just go ahead and integrate both sides now, we're going to integrate the left side of the equation with respect to y. We're going to integrate the right side of the equation with respect to x. So let's go ahead and do that. So in integrating the left-hand side, I'm just going to rewrite this exponential since we have an e to the minus y sitting there in the denominator. I'm going to use algebra, and because I have that e to the minus y in the denominator, I can move that up into the numerator by changing the sign on the y. So this is equal to e to the positive y if we moved it up into the numerator, and that's dy. On the right-hand side, well, we can just keep this as x squared minus 1 dx. And now both sides of this equation, we can pretty much just integrate in a straightforward fashion, but you could imagine that at this junction, now that we have two integrals to consider, we might get to use things like integration by parts, we could use trig sub, partial fractions, any of those old goodies from our integration toolbox. So let's mosey on along. So on the left side, the integral of e to the y is just e to the y. still the best function that there is. On the right-hand side, we really get to apply the antiderivative power rule. So we have a 1 over 3 x cubed minus x. However, the last little bit we need to add is, of course, our integration constant plus c. Okay, so we are not completely done yet. For example, even though we finished integrating, we basically have a solution to this differential equation. But we can do a little bit more algebra to try and solve for y as a function of x directly, as opposed to just having a function of y equaling a function of x on both sides. So let's go ahead and try to solve for y by itself on the left side. And remember, whatever we do to one side of the equation, we get to do to both sides of the equation. So how can we get that y by itself? Well, the first thing we could do is, I'm just going to copy this line down again, is we could take the natural log of both sides of this equation. So I'm going to come across here, take the natural log of the left side, take the natural log of the right side as well. And now you might remember from log rules, when we have the ln of e to some power, well, that'll just bring that y out in front. So the left-hand side is, well, ln of e, but where that y comes is out in front. The right-hand side can just stay the same. It's still the ln of that entire thing, 1/3 x cubed minus x, and we still have the plus c inside of that natural logarithms argument. So the plus c is still inside that natural log. So we're almost done with solving for y directly as a function of x, because ln of e, well, that's just defined as the number 1. So the left-hand side of our equation just becomes y. And the right-hand side as well, it's ln of 1/3 x cubed minus x plus that integration constant c. And this is what we call an explicit solution to our differential equation. And it's called explicit because we explicitly have y on the left side equaling a function of x on the right-hand side. But the last thing we still have in this problem is we do have this plus c term. And remember, this plus c is that integration constant that we've been lugging around for a while, or that plus c we've been tacking onto all of the indefinite integrals we've been doing. But we can actually figure out what the plus c value is, or this value of c, by using our initial value. So if we scroll back to the beginning of this problem, we had this other piece of information that we were given that we never used yet. We were told that y, when x equals 0, is equal to 1. So I'll just rewrite that here. We were told that y of 0 is equal to 1 in this problem. So what that means is we're going to take our solution that we just found and plug in anywhere there's a y, we're going to plug in a 1. Anywhere there's an x, we're going to plug in 0, and then we're going to see what we get. So let's go ahead and do that. So again, anywhere there is a 1, we plug that in for y. Anywhere there's a 0, or anywhere there's an x, we plug that in as 0. And now what you notice is the last unknown thing we still have, that plus c, we fully can figure out what it is in terms of a numeric value. The left-hand side of this equation is just 1, and the right-hand side, if we simplify it, turns into, well, 0 cubed is 0, minus 0, so we have the ln of c is equal to 1. And if we wanted to, well, we could figure out what c is directly here. To figure out c directly, I'm just going to rewrite this equation down below. We exponentiate both sides to get c by itself. And that's really a fancy way of saying, hey, both sides of the equation, we're going to raise e to both sides of that equation. So the left-hand side, e to the first, that's just equal to e. E to the ln of c, well, that's just giving us back c. So we figured out in this problem, the value of c is actually equal to the number e. So the last thing we get to do is go back to our solution that we found, that explicit solution, except anywhere there's a c, we can replace that with our e. Because we just found the value of c in this integral, or this case, is equal to our constant e. And that is our explicit solution to this differential equation. Remember, the name of the game was using the method of separable equations, which meant we got all the y's on one side of the equation, then we got all the x's on the other side, which we did in this step to this step here. We integrate both sides of the equation. The left side we integrated with respect to y, the right side we integrated with respect to x, and then we did a bit of algebra, and we're able to figure out what y was by itself on the left-hand side, which made this what we call an explicit solution, except we still had that unknown integration constant c to find out. And the way that we found out the value of c was using that initial value that we were given at the beginning of the problem.